Yeah, so I'm Joseph McPeak. I'm here to manage the Novo Nordisk Pulse EPR Center here at the university. I'm also currently still a guest scientist in the department Spins and Energy Materials at the Helmholtz Center in Berlin. And today I want to talk about my previous research in electron paramagnetic resonance and also show a brief introduction of how the technique works. And hopefully you'll come away with some interest in incorporating EPR into your research. My screen has a little bit of lag. Okay, so my sort of education and background, I was born in Fort Smith, Arkansas, which is this state in the central part of the southern United States. There, early in my career, I attended trade school to be an auto mechanic, where I specialized in electrical systems. I then decided that I didn't want to work on cars for my entire life, so I moved across the state, just over the border to Tennessee, where I did a bachelor's in chemistry, researching analytical chemistry with John Russ at Rhodes College. There, we investigated carbonaceous materials that made up some cave paintings in southern Mexico. And we demonstrated that the constituents were viable for radiocarbon dating in those cave paintings. So that was a nice, fun project. I then decided that I really enjoyed research. So I moved to Denver in the Rocky Mountains to pursue a PhD in chemistry at the University of Denver. And there I started my career path in EPR development, working with Gareth and Sandra Eden. Following my PhD, I then moved to Germany to start a postdoc in Berlin, developing EPR on a chip technologies, as well as to study energy materials in the Department of Glass Lips. So now I am in Copenhagen, as you all know, where we have a Pulse EPR facility that Sturgis has received funding to start. We've just recently installed the instrument 2 months ago, and we're up and running quite routinely now. I joke that when Sturgis wrote the proposal, this instrument was supposed to be the first Pulse EPR spectrometer in Denmark. But you can see that I'm, settling into the department quite well, because I already have a colleague and now rival in Aarhus, Willy, in the group of Niels Christian Nielsen, who just 1 month before we installed the instrument sent me this lovely FID of a pulse experiment he did in Aarhus. So that's well and good. We are officially the second Pulse EPR spectrometer in Denmark, but we are the only Pulse EPR facility that's open to external users. So a little bit about our instruments. We can perform X and Q band measurements at variable temperature between room temperature and 4 Kelvin. We can utilize radio frequency excitation to play with nuclear spins, modulating our electron signal. And we also have an arbitrary waveform generator for mixing and doing somewhat exotic pulse sequences and pulse shapes, trip pulses, things like that. The formal commitment for half of the year for the facility is to research quantum materials, semiconductors, catalysis, and 2D nanoscale materials, governed by the letters of support for establishing the facility. But the other half of the year will be reserved for open calls, both within Denmark and outside of Denmark. So hopefully we will organize a call for proposals soon. So if you see something today that piques your interest, I encourage you to contact me, and we can get together and see how EPR can benefit your research. So a brief tour de force of my experience and research in EPR development. One of my first projects here on the left, back in 2016, was investigating the resulting signal in carbon materials from gamma irradiation. And so here you can see we get an increasing dose response from increasing gamma irradiation. We found that an EPR technique called rapid scan that the Edens developed in Denver could utilize rapid passage in a way that elicits a much greater signal response relative to the traditional technique shown here. This is a direct detection technique, so we're not using lock-in detection. You get a pure absorption signal instead of a derivative signal. And here you can see that we demonstrated that the SNR, or signal-to-noise ratio, of our technique versus what was conventionally done in the literature was vastly improved. Next, I studied these frustrated Lewis acid pairs containing a boron heterocycle here. And we found that the single electron was primarily concerned about the boron, but it can sort of move around this entire molecule. And through some electron spin echo modulation and continuous wave with simulations, we found that we could fully characterize all of the hyperfine couplings within this molecule. I then moved to what the bulk of my PhD was concerning, and that's the development of a saturation recovery spectrometer. And here I've shown you the bridge and one singular data set, probably too small for you to be able to see. But this was the bulk of my PhD research. We first, in conjunction with the engineers at the University of Denver, created a cross-loop resonator that isolated excitation detection. We then utilized the spectrometer to characterize some molecules for dynamic nuclear polarization experiments. We finally, having already published 2 papers, decided to publish the design and implementation of the instrument, and then later utilized it to investigate isotopically labeled small molecules, radical containing spins there. So what the instrument does is it measures spin lattice relaxation, and this is a technique called saturation recovery, which is unique to typical spin lattice relaxation measurements because we can measure T1, or spin lattice relaxation, free of spectral diffusion artifacts. And so that's very useful when you have a situation where your T2 or spin-spin relaxation is so fast that you can't observe an echo by traditional pulse EPR methods. And with this, we can extrapolate a T1 without the need to modulate T2. I then moved on to do some lanthanide experiments, studying the relaxation behavior of free ion lanthanides in water ethanol solutions. And we wanted to see how the relaxation changes with respect to temperature over what we would consider a broad range of 4 to 10 Kelvin, which many of you perhaps wouldn't consider so broad, but we had, this is a log scale here, and we saw quite some change in the relaxation rate over this narrow temperature range. I then transitioned to my postdoc, where I developed and investigated EPR on a chip technologies. So here we've miniaturized the EPR spectrometer to a 12-coil voltage-controlled oscillator array. And here this chip measures about 1 millimeter by 3 millimeters. And with this, we can perform similar spectroscopies that I was working on in 2016 here. And here you see when we utilize rapid scan with this small EPR on a chip, we can still get this vast improvement in signal-to-noise ratios. I then, with my colleagues, wanted to study semiconductors using the EPR on a chip. So we measured electron-detected magnetic resonance in silicon solar cells. And this technique is a bit different from traditional magnetic resonance, where you are instead using the magnetic resonance interaction to elicit a spin flip, which then subsequently elicits a current change in the device. And you can measure this in a similar way to detecting EPR signals, but instead use a transimpedance amplifier in your detected current. So that allowed us to measure current limiting processes in solar cells. So now that I've given you an overview of what I've worked on for the last years, I want to take a step back and just start at the basics. So when we're speaking of electron paramagnetic resonance, we're speaking about measuring the absorption or dispersion characteristics of unpaired or conducting spins. So when you take a molecule like this nitric oxide diagram, we have a single unpaired spin at the highest occupied molecular orbital here. This spin contains a charge and angular momentum, so we have a small molecular magnet. This is what we measure in EPR because we can input energy and elicit a spin flip. Now, analogous to NMR, organic radicals will have what we could consider a small chemical shift relative to the free electron d value, but we can also measure unpaired electrons in transition metal ions, where you have larger spin systems, and these have a whole magnitude of varying deviations from the free electron g value. So what we actually measure here is that spin flip, the absorption of energy at the resonance condition. So when you have a single unpaired electron, its direction, spin up, spin down, is degenerate unless you apply a magnetic field. Once you apply a magnetic field, you align the electron either with or against the field, and that creates a separation of energy. When you have this separation of energy, you can input energy at the resonance condition, and elicit a spin flip governed by the Zeeman interaction here, which is related to the input of energy at a frequency taking place at a specific magnetic field governed by the lambda G factor. When all of this happens, you can elicit your spin flip and have this transition between energy states. So here graphically, we're showing a transition between the -1/2 and the +1/2 energy states while sweeping the magnetic field at a constant frequency. And here would be your resonant absorption. What this looks like on our detector is either an absorption signal like this at the top, or a derivative signal if we use lock-in detection. So we can measure a lot of different electronic interactions with EPR. We can, the primary measurement that we make is the electron-Zeeman interaction. This interaction can also be modulated by nuclear Zeeman interactions, which are then subsequently modulated by hyperfine couplings, which give a measurement of strength of coupling between adjacent nuclei to the spin center. And then in very complicated cases, we can have nuclear quadrupole interactions, which start to take into account the asymmetrical electronic dipole distribution in nuclei. All of these can be investigated by EPR, such that you can get some very complicated spectra rather quickly. And so if you have all of these interactions, you can maybe find yourself in a scenario where you have this nice sample that you want to measure by EPR and learn something about your system. But when you start to consider that your electron Zeeman can have multiple spin states and transitions, those can all be modulated by nuclear Zeeman interactions at varying hyperfine coupling strengths. They can also be dipolar coupled to an equivalent system of similar complication and complexity. You can have additional complexities like zero field splittings, anisotropies, and homogeneities. And from all of that, you might put your sample in your spectrometer and get a very rich, vibrant spectrum like this that ranges a very wide field range. However, when you look into the literature, it might be the case that you find, rather than measuring your sample of interest, you find that you've measured the diatomic oxygen that has pilfered its way into your test tube. And instead, you might flip the table and decide that you never want to use electron paramagnetic resonance for anything in your research ever again. So hopefully that's not the case, and I can convince you over the next few slides as we build up from the most basic spectrum to something complicated, that interpretation of EPR spectra is not so complicated, and you should use it in research. So let's start with the building blocks here, and let's just take the basic free electron EPR spectrum that I've simulated here. I've made these simulations with the help of a nice program by the author Stefan Stoll at the University of Washington, US. He has a vibrant library of EPR tools for interpreting your spectra and simulating what you see on your detector. So here I've simulated a spectrum at the most popular operating frequency of 9.5 gigahertz. The lambda G factor is 2.0023 for the free electron. It encompasses just a single component of narrow line width and is isotropically tumbling, which means we spherically average over the entire molecule. Here you can see that you get just one line, and your spectrum is relatively simple to interpret. And this really occurs in many radicals that we study. Carbon-centered radicals that are considerably isolated from your environment have this type of spectrum, and you can learn quite a bit, even though it looks like a deceptively simple spectrum. If this spin is interacting with a nucleus of spin 3 halves, you get a hyperfine coupling of arbitrary value. Here I've input 50 megahertz, and you can see that your I equals 3 halves interaction splits your single line into 4 adjacent lines. Now here we're still in the isotropic regime where everything is spherically averaged, so your lines are evenly spaced and symmetric intensities. And here, if you look carefully, you can actually measure the distance in between these lines and directly read out your hyperfine coupling strength, which is a relatively simple experiment, but can also be quite powerful if this is what you're interested in mapping an isotropically tumbling system, trying to withdraw spin couplings in that way. Now we complicate things a little more by adding a second weakly coupled nearby nuclei, an I equals 1 nucleus with a hyperfine coupling of 12 megahertz. Now we have this strong dominant coupling of 50 megahertz, splitting our single line into 4 lines. And then our weakly coupled I equals 1 nucleus, splitting all 4 of those lines additionally into 3 lines each for a total of 12 lines. Now here, you can actually still, if you're careful, read off the coupling strengths by measuring the distance between the weakly coupled lines, and then treating all of those as a unit. You can measure the distance in between units and withdraw both of these coupling factors. So things, while they start to build in complexity, are still relatively simple for interpretation. However, when we now incorporate 4 equivalent I=1 atoms, each with this weak coupling of 12 megahertz, we start to complicate things because you're no longer experiencing lines of all the same intensity. And this is governed by the overlap here, shown best by an example of Pascal's triangle. So what you see here is that some of the lines, when you have equal spacings, will overlap and start to build in like a 1-3-3-1 pattern. But when you have 4 of them that are already split by an I=3/2 nuclei, excuse me, things are getting rather complex. But we're still isotropic, and you could, with a simulation program, relatively simply withdraw your relevant parameters from the spectrum after you're familiar with seeing this type of spectrum. Lastly, the most complicated interaction that we can incorporate into our spin system using this now not so simple example is anisotropic interactions. Now here we consider that the molecule is no longer isotropically tumbling or spherically averaging, and instead the spin-containing dipoles are now oriented in the magnetic field in a way that's anisotropic, meaning that you have a directional component. When you're aligning with or against the magnetic field, you then get differences in absorption, and you can see that an axial symmetry-like molecule will have an EPR spectrum that's roughly like this, and that's somewhat similar to what we've seen here. And in this case, you can still withdraw some of your hyperfine interactions from the spectrum directly, but things get much more complicated. But you can still simulate this using software, and it's relatively straightforward once you've accustomed yourself to the different types of EPR interactions. So here, I'm using that same example that we've built up slowly over the last few slides. And in fact, this is a popular spectrum and popular topic of research concerning copper imidazole type molecules. And here, this group in 1987 shows a very similar spectrum, but they've utilized the very information that we've been building up slowly over the last few slides to understand something about the binding environment of this copper imidazole species. And this is all well and good, and a very nice example of how you can start with the basic building blocks and build towards something that's very useful for real-world research. Now, I want to take you through 2 examples of my research and show you how I've used EPR in some fun ways to tease apart structure and function analyses in different investigations. The first I want to show is a mechanistic investigation where we tried to discern the mechanism of this intermolecular samarium cyclization, samarium-mediated cyclization, where we have this starting material 1, this alpha bromo ketone, and this cyclized aryl ketone here, mediated by samarium diiodide reduction. Now, to perform this reaction, you require 2 equivalents of samarium, indicative that you're having 2 single electron transfer reactions. So my colleagues and I hypothesized that, or postulated, there were 2 viable radical intermediates that could be the intermediate mechanism towards the successful product generation. One where the single electron species is first deposited at the ketone, and one where the bromine is instead liberated first and a radical appears on this alpha carbon. So we're focusing on these 2 intermediates, and by the last few slides, hopefully I've convinced you that these would have different hyperfine interactions based on the nearby nuclei. In intermediate 6 here, there's no protons near this radical because this carbon has no protons. However, in intermediate 8, we would have 1 proton here, so we would have an I=1/2 interaction, and our single electron species would be split into 2 lines relative to a purely single line shape observed here. That's only if we could observe either of these species by themselves. However, this reaction occurs rather quickly, and it's far too fast to observe with traditional EPR methods. So what we can do instead is to perform spin trapping. In spin trapping, we take an adjacent molecule that can absorb a radical and form a spin radical adduct, which is a combination of these 2 species that is then much more stable than the milliseconds to microseconds that the reaction intermediate is. And so here we have this nitron bond that then absorbs a radical such that the radical that's trapped is then primarily located on this nitrogen-oxygen bond. And you start to see hyperfine coupling from the adjacent proton in both of these examples. So here I've shown or simulated a very simple example of what either of these 2 spin trap radicals would look like. And you get coupling to the nitrogen, which is I=1, splitting into 3 lines, your single spin. and then an additional weak coupling to this adjacent proton, splitting each of those 3 lines into a further 2 lines. And so you can use this to trap your radical, but you don't always get such useful information because you only get how this R group affects these 2 hyperfine coupling constants. So what we instead did is we utilized a rather unique spin trap, which is not so stable, but was stable enough for our research, mononitropropane, which you can see only has the nitrogen and no adjacent protons for coupling. So when we utilize this species to trap either intermediate 6 or intermediate 8, we will still see the 3-line spectrum from the nitrogen coupling, but we will either see no additional coupling or an additional proton. So when we did this experiment, in the presence of our spin trap agent, we recorded this spectrum here, where you can clearly see that there's the 3-line spectrum, further split by into two lines from presumably a proton here. Now, we thought this was a pretty good success, but we weren't completely convinced. So my colleagues selectively deuterated this proton here, and we utilized this material to repeat the reaction. And what we found was that our 6-line spectrum collapsed into 3 lines. Now we can calculate this collapse because when you go from a proton to a deuterium, you switch the nuclear interaction from an I equals 1/2 to an I equals 1. And what you might think, if you've been paying attention on the previous slides, is that if you move to a larger spin order about your nuclei, you increase your number of lines. But what we know from the literature is that the coupling strength, the magnitude of the hyperfine coupling, when you switch to a deuterium, often decreases by about a factor of 6.5. So here, rather than seeing 9 lines, which is what we should see from 2 I equals 1 couplings, we instead see only 3 lines from the nitrogen. And the deuterium has such weak coupling strength that the 3 lines that should be present here are just broadened into a single wide line. So all of that to say, with reasonable confidence, we were able to conclude that pathway B here and radical intermediate 8 are how the reaction proceeds, and we were able to publish this work in the Journal of Organic Chemistry in 2018. Now, we can also measure transition metals and F-block metals. Here, samarium begins its life as samarium-2, but we could reasonably monitor the conversion from samarium-2 to samarium-3 because samarium-3 plus is EPR active. And we've done some relaxation measurements with samarium-3 plus that we published in a separate volume. However, this requires some freeze quenching of the reaction to get any useful sort of rate information, and that was beyond the scope of our study. But it is something that you can do, and many groups do these freeze quench procedures to measure the reaction rate of their catalyst or other intermediates. So now I want to shift gears and talk about photocatalyst investigations. In my work as a postdoc, I was able to collaborate with the Shalom group at Ben Gurion in Israel, where they are primarily interested in carbon nitride materials. Carbon nitride materials are these fascinating carbon-nitrogen triazine unit-like materials that can be used for a variety of different interesting reactions for us. They can be used for hydrogen production via water splitting. They can be used for CO2 reduction to carbon fuels, such as ethanol and methanol, methane. And they can even be used for environmental remediation, getting pollutants out of our water supply. These are really nice materials that can be easily synthesized from earth-abundant materials like melamine, urea, cyanuric acid, anything with stable alternating carbon-nitrogen cycles. However, their efficiency limiting processes are not well known. So that's what we wanted to study. So how this material works is it has these alternating triazine units that form these sheet-like structures of varying morphologies. When you shine light onto these materials, you can promote electrons from the sigma-type bonds in gray to the conduction band pi conjugated structure here shown in green. And then that energy can be used for various catalytic reactions. So when you read the literature or when you freshly synthesize this material, you find that the conduction band is typically characterized in EPR by a single wide Lorentzian line shape shown here in green. However, what we found during our investigation is that as time goes on, as early as 2 months, but very much present after the first year, this material has a defect center that grows over time, and it's this narrow line shape shown here in blue. So we wanted to try and understand how this defect signal affects the catalytic capabilities of this types of materials. So the first thing we did is to investigate the light determining processes of the material after the defect has been generated. So here what we did is we did our EPR experiments while shining wideband laser light into the resonator. And what we found here when shining either 400 to 500 nanometer light, 500 to 600 nanometer light, or 600 to 700 nanometer light is that the EPR intensity in all of our materials increased, particularly when we did simulations, only on the wide peak that we saw in the previous spectrum. So what that tells us is that after simulation, we found only the wide peak increasing and the narrow peak being relatively inert, confirming that the wide peak is still photocatalytically active, while this defect center is doing nothing for us and not generating any energy from light whatsoever, which was a relatively important finding for our study. We then wanted to try and characterize this defect center relative to its wider counterpart a little bit more intensely. So what we did are some relaxation experiments to try and determine spin-spin relaxation in both of these species, but you can see that they overlap quite considerably. So real quick, there's a nice animation that shows you how the pulse experiment is done to detect T2 relaxation. It's different from the spectra that I've shown you so far, because you, instead of applying a continuous microwave, you instead do an inversion pulse here that then refocuses your spins. And as you space your inversion pulse from your excitation pulse, you get a decay in this echo that gives you an estimation of your spin-spin relaxation time. Usually this interaction is monotonic, but in our example and materials where we have overlapping spin systems that are somewhat isolated, we assumed, we were able to fit our data that we obtained with a bi-exponential model and withdraw two very separate time constants, indicative of two very different species. So our first species we isolated to around 500 nanoseconds to 1 microsecond in relaxation time, and our second species was much slower at between 1.5 and 5 microseconds. And this will be useful information for our characterization. So second, we wanted to determine how the defect was being generated in our material and if it was detrimental for catalysis or not. So what we first did was postulate that because we've been storing these materials on the bench open to the air, that oxidation might be a problem generating this defect. And what we found when we kept our pristine materials exposed to a purely oxygen environment, that we could rapidly increase the rate of defect generation, such that we increased our defect center signal by quite some magnitude on the order of days rather than months that we had seen on the benchtop, and that we were decreasing the number of spins available for photocatalysis. We wanted to further confirm this by exposing our system to hydrogen peroxide. And what we found when we exposed it to hydrogen peroxide is that we completely destroyed the spin signal from our photocatalytically active peak, and yet we still had this very sharp impurity or defect signal found in our previous parts of the study. So having a pretty good idea of how these defects are generated, we then sent our materials back to our collaborators in Israel and found that if they compared the catalytic outputs for the H2 evolution reaction with freshly synthesized material and the materials that we had been studying, these defects present, they found a considerable reduction in some of the materials in terms of catalytic output. Now, all of this allowed us to postulate, both with the relaxation behavior and the way that spins would be introduced into this molecule, that the likely series of events here is that in your pristine material, you have this intact photocatalytically active pi conjugated structure that then, via single electron transfer from oxidation interactions, creates an additional species, likely carbon-centered, based on our relaxation data, which then is of great detriment to the available area for photocatalytic activity in this pi conjugated structure. So with all of that found, we were able to publish these results in Molecules just this year. And now what the group in Berlin is studying is how the transition metals that are incorporated in these materials by our collaborators at Ben Gurion act as either a modulation or a protective inhibition of this oxidation reaction just by having the metal sitting in the core of the triazine units. Of course, research is not that straightforward, and in principle, the metal doesn't sit right at this core, which is postulated in the literature, so we're also trying to uncover some of those interactions as well. Now, getting back to the Pulse facility here in Copenhagen, I hope I've convinced you both by building up some simple spectra to some more complex research relevant spectra and showing you some examples in my own research that EPR is a great tool for understanding structure-function relationships in all kinds of materials. It's highly selective for single spin species, but it's not selective in between single spin species without doing some interesting tricks. But because we have this nice pulse instrument, we can play a lot of tricks and try and get to the root cause of structure-function relationships in many materials. So quickly recapping the instrument capabilities that we have and the research areas that we want to extend into, we can do a multitude of experiments that should be interesting for you and in many ways can benefit your research. So my question as I conclude is how can EPR be used in your research? And I hope that you can, of course, answer at the end of the talk, but I also hope that you will email me and bring me lots of interesting spectra that you find in the literature and ask me how you can incorporate this into your research, how you can do similar experiments to get valuable information. And hopefully, if all that goes well, we'll translate that into some effective proposals and start making good use of the center here. So as I conclude, I need to thank everyone that's been involved in the research, my magnetic resonance group at Helmholtz, all of the people involved in that research, the Anders group at Stuttgart for making our chips that I utilized in some of my research, the Shalom group that fabricated our carbon nitride materials, and the Cowan and Eden groups at the University of Denver for the mechanistic investigation with samarium iodide reductions. And of course, I'm very thankful to all of the funding sources that I've had the privilege to work on projects under through many of these different groups. Lastly, I want to do a quick plug for the International EPR Society virtual seminars. If you're interested in learning more about EPR, the advanced techniques, how it's employed in various research environments, we do a bi-weekly seminar that incorporates both tutorials and students and postdocs showcasing their work. We do this continuously through the academic season, and currently we're in the middle of our fall schedule. Our next talk will be on the 1st of November, and this occurs at this week at 2 p.m. local time here, but I think following weeks it will be at 3 p.m. As the US changes its time. So if you're interested in that, go to this website or drop me an email, and we can get you more involved and get you more information about EPR spectroscopy. So with that, I'll leave the information about the center up and we can transition to some questions. Thank you for your attention.